Okay, hey, welcome back. We're going to start integrating over surfaces. So just to recall what we've been doing, we first integrated over curves or on curves. So we saw the integral of ds, which is basically just going to be the arc length formula. And that would give us the length of the curve. Uh, so before, kind of, we had this guy. And now for surfaces, we have the double integral of s d big S. And of course, to evaluate this arc length thing, we would have to parameterize everything. You would end up with I believe, the integral of the square root of x prime of t squared plus y prime of t squared dt. And this thing right here, of course, is just the magnitude of r prime of t. But yeah, okay, we get it. Right, so now the formula that we're using, we kind of have to put this into terms, and this would have been it from a to b. We think of this as integrating over some region r of the square root of 1 plus the partial with respect to x squared plus a partial with respect to y squared times dA. But we also thought now in a parametric form where to evaluate that version, you would integrate over some region D in the UV plane, and the formula then in that case would be R with respect to U cross R with respect to V dA. Okay, so we didn't really start with this formula before. I don't think we started there exactly. I mean, we did kind of technically because we had seen the parametric form way back in Calc 2. At the end of Calc 2, they actually introduced that. But where we started before in section, was it 15.2, was actually integrating some function like f of xy over some curve, right? And then of course to evaluate that, we would maybe have to parameterize f of it would be x of t comma y of t, and then times the square root of x prime of t squared plus y prime of t squared dt from t equals whatever to whatever. So the only difference is basically we're tacking on this additional f of xy part right into here. So what we want to do then now is kind of the same idea. We want to tack on some function in here, okay, in the inside of these integrals. So now what we'll be doing is basically doing an integral over a surface, and visually it's no big deal. It'll just be plopping this function f of x y z into here. No big deal, right? And then to evaluate, we'll have to probably parameterize it, but first we would have to rewrite it as an integral over a region of f of x y z times the square root of 1 plus the partial with respect to x squared plus the partial with respect to y squared dA. Then in the parametric form, we'll also have to deal with that. So you would end up with some r of uv function plopped in here, ds. And then to evaluate that, of course, we have to convert everything over, and we can kind of start at the same place. Let's not put r of uv. Let's put f of x y z ds, and then we'll convert it over to our uv plane by doing substitution. So you'd have f of x of uv comma y of uv comma z of uv, and then this would be the magnitude of ru cross rv dA, which is du dv or dv du. Okay, so again, it's basically all we're doing in this section is integrating over a surface by kind of plopping in plopping in a function in our integrals. Okay, so I mean, I don't want to say visually because I don't want to mean geometrically. So, but this is kind of the idea. Okay, visually, what's happening is that we are kind of uh, okay. So for the if we get a surface z equals f of x y, let's go to our, I guess, Twinkie in space. Oh gosh, I just ate something. Sorry, it's not agreeing with me. Something like this. And we're here. And of course, there's the projection of it into the XY plane here. And we're, chopping that up into a bunch of sections and then maybe considering one particular part of the surface. Maybe that part is the result of projecting this part onto the surface, or onto the plane rather. So what we're doing is kind of this guy, we're approximating that with the tangent plane, recall. So maybe this is kind of like this curled type plane, and then we're attaching tangent plane. So we'll approximate this surface, which we call change in s sub I, with this change in t sub I. But on top of that, we're going to also kind of attach some functional value. Okay, so f of x, y, z on top of it. So geometrically, what that is kind of the volume of a cube sticking out of it, right? Because it'll be basically the area of the little tangent plane times some f of x, y, z, which will give you basically the volume of that cube that's attached to the surface. So that's kind of what I mean by you're integrating over the surface, right? And let's see how yeah. So you're forming this new kind of increment. I guess I'll call it delta. I don't know what to call it at this point. Delta big Z sub I, which we'll say is f of x sub I, comma y sub I, comma z sub I times we wish the change in s sub I, but of course we're approximating change in s sub I with that crazy square root thing, and then we're summing across over the surface and getting our sort of integral as we take the limit as the norms of the rectangles in the xy plane go to 0. Okay, so we'll have the sum of these f of x sub I, y sub I, z sub I, change in s sub I, and as the limit of the norms goes to 0, you'll get the integral du jour, the double integral over the surface S of f of x, y, z. Okay, and what I'm saying is it's basically very similar to what you did before with an integral of a function over a curve in maybe like the xy plane. Right, so if you're here in the xy plane, you have some sort of curve, and maybe you can imagine attaching a function to it is kind of like figuring out the area of this of a wall that's built on top of the curve. Just like here, it's going to be a volume kind of scenario. But yeah, that's it. I mean, you're adding up this function over the surface. You can do whatever you want with it. You can do mass, figure out that sort of thing. Okay, so anyways, let's look at some of these problems. Okay, so without further ado, maybe we should look at some of the problems in the homework. So we'll do this, and then we'll also have to do the kind of the vector versions as well. Okay, so do recall that we also did that in the line integrals. We had the vector version. Okay, so also then And I'll remind you of this when we get there. We also looked at the integral of the vector field F on the curve C. Okay, and we'll have to develop some formulas for that as well in this new context. Okay, so anyways, the beginning problems, like number 2, we're figuring out the surface integral, the integral of x minus 8y plus z over the surface. It's the integral of x minus 8y plus z over the surface given by these formulas. Z equals 9y. Okay, and then we're restricting x and y to be from 0 to 2, and then for y it's from 0 to x. Okay, so z equals 9y, that's just a plane, and then we're integrating over let's see, 0 to 2, and then 0 to x is just this line. Okay, so we're integrating over this little triangle region. I'm not going to try to draw the surface, but we do need our partial derivatives. So z with respect to x is just 0, z with respect to y will be 9, and then we'll have the double integral of x minus 8y plus, and we have to rewrite z so we can do this double integral. Z is equal to 9y, so plus 9y, and then it'll be dy dx, and of course then y goes from the line y equals 0 to the line y equals x, so 0 to x, and then x is going from 0 to 2, and we should be able to just go at it then. Whoops, I forgot the square root part. Sorry about that. So got to tack that in as well. So you have the square root of 1 plus z sub x squared is 0 plus z sub y squared is 81 dy dx. And so you could factor out the square root of 82, and 8x minus 8y plus 9y is x plus y dy dx. So this will be square root of 82, double integral. Well, let's go ahead and integrate with respect to y. So we'd have xy plus y squared over 2 times dx, and we have to evaluate that from 0 to x. So we'll end up with square root of 82 times the integral of x times y is now x, so x squared plus x squared all over 2, and then minus 0. We can simplify that, so it's square root of 82 integral 2 halves plus 1 halves is 3 halves, so I'll have a 3 halves x squared dx. You can factor out the 3 halves, you get 3 square root 82 all over 2, and then I have to integrate x squared, so that's going to be x cubed all over 3 from 0 to 2. The 3's cancel. I'll have x cubed all over 2 from 0 to 2, and I still have a square root 82 floating about. And then 2 cubed is 8. 8 divided by 2 is 4, so I'm getting 4 square root 82. Okay, so pretty simple, so long as you don't forget. It's remembering all of it, you know, on a test. It's like, oh, I'm going to remember all this. Like I said, you could do applications with this. Find the mass of the surface of lambda s density rho. So basically for number 4, I'll just set it up, I won't do it. We're integrating over the surface given by this plane, 2x plus 3y plus 6z equals 12. And then we want to work with this character here, x squared plus y squared. And so my double integral will be of x squared plus y squared over this region. So I'm going to rewrite it. So 6z equals 12 minus 2x minus 3y divided by 6. 2 minus x over 3 minus y over 2. And then I need zx, which will be what? Negative 1/3, and then zy will be negative 1/2. So it'd be x squared plus y squared times the square root of 1 plus 1/9 plus 1/4, and then your dy dx. We need to get the projection of the surface into, I think it said the first octant. Yeah, so they want the mass of the surface lamina S of density rho in the first octant. So you're thinking the projection into the xy plane. Let z be 0. So if z is 0, you'll get 2x plus 3y equals 12. So you'll have 3y equals negative 2x plus 12. So you get y is negative 2/3 x plus 4. So in the first quadrant, it seems I am going from 0 to that thing, right? If I graphed it just in 3 dimensions, you could kind of see it. So I just want to make sure I'm not getting the wrong region. When x and y are 0, z is 2. When y and z are 0, x is 6. 2, 3, 4, 5, 6. And then when x and z are 0, y is 4. 1, 2, 3, 4. So that's our surface. And of course, in the first quadrant, it's just this triangle region that we're integrating over. So, sure, it'll be 1, 2, 3, 4, 5, 6, 0. And then on the y-axis, 1, 2, 3, 4. So it's this region. So I'm integrating from y equals 0 to y equals negative 2/3 x plus 4. And then x equals 0 to x equals, I said 6, right? So 0 to 6. This integral looks pretty nasty to me, believe it or not. It just looks like a freaking nightmare. I have to FOIL. It's not that bad. You just have to FOIL out, and that's going to be nasty with that fraction. So it won't be so bad. But you know, you can always check your answer before you submit by going to like Wolfram and then typing it in and making sure you get the right answer, right? So int of x squared plus y squared. And I honestly would not even put that square root junk in there. I just tack that on at the end. So x squared plus y squared, comma. Looks like I'm going y equals 0 to negative 2/3 x plus 4, comma, x equals 0 to 6. Push enter. This razzmatazz right here is going to be the square root of 36 plus 4 plus 9 all over 36, which is 49 over 36, which is 7/6 once you take the square root of it. So this answer should be 7/6 times 104, and whatever the heck that is, right? So 7/6 times 104 is, drumroll, 364/3. And let's make sure, yeah, okay. So, you know, if you want to, before you start, you can kind of see what it's going to be, and you'll know then if you made any mistakes in your work. Okay, so some of the integrals can be kind of nasty. Again, I don't want to bumble through one for you. I've already done that. You don't know if there's much to learn by seeing me make a mistake, right? So anyways, now we want to consider the other form in parametric, the parametric form. And again, all you're doing is kind of slapping in this function and you're integrating over it. So I kind of didn't even set up a section. I feel bad for that. So let's call this first section section 1, z equals f of xy, and we're doing surface integrals on that. Section 2, then we're moving into the parametric form. Okay, so the surface integral in this case will, again, f of x, y, z ds. So you're integrating that function on the surface, and then to integrate it, we're going to reparameterize everything in terms of u's and v's. And instead of that square root 1 plus fx squared plus fy squared, it'll be the magnitude of the cross product of RU and RV dA, right? And we're integrating over some weird region in the UV plane. So let's see if we can get our hands on one of those. Sometimes you got to go polar, go convert the polar to evaluate some of these. We'll just try number 5. So I have the double integral of s of y plus 4 ds, and the region, or rather the surface, is going to be u comma v comma 5 v, and then the region we're integrating over in the UV plane is some box, right? 0 to 1 of the u-axis, and then 0 to v to 3 on the v-axis. So it's this box we're integrating over. Okay, so I need to get the partial derivatives and then their cross product to pull this off. RU will be 1, 0, 0. That should be painless. RV 0, 1, 5. And the cross product equals, cover up the first column, 0 minus 0. Cover up the second column, minus 5 minus 0. Cover up the third column, 1 minus 0. So this will be 0, negative 5, 1. I need the magnitude of that for my integral. So that's going to be square root of 25 plus 1, which is square root 26. Stuff it all into my integral now. So I'm integrating over this region D. I'm going to rewrite this u plus 4 now using our new parameterization. Y plus 4, I'll write that y is v, so I have v plus 4, and then times the square root of 26 times d, we'll go v and then du, right? So we'll do dv first, and of course the bounds on v, u the 0 to 3, the limits on the inner integral is 0 to 3, and then the outer one 0 to 1. So I can factor out the 26, and I'll have v squared over 2 plus 4v du, and then I'll have square root 26 integral of, did I just integrate that? Oh, I didn't mean to integrate that already. Okay, so I integrated. I just have to evaluate on 0 to 3. So I have then, putting in 3, 9 halves plus 12, which is really 24 halves du. That will be 33 halves times the square root of 26 times the integral from 0 to 1 of du, which of course will just be u evaluate from 0 to 1 will be 1, so I'll just have 33 halves times the square root of 26, which is the right answer. Okay, so now we want to we have basically, we're doing integrals of a function over a surface. Okay, in 15.2 we did integrals of a function on a curve, but we also did integrals of a vector field on a curve. So now we want to do an integral of a vector field on a surface. right? So first things first, we need to kind of define just what exactly we're after. Um, and in order to pull this off, we're going to have to talk about orientation. When we dealt with our, so let's make this section, I think it's 1, 2, 3 now. And we're dealing with vector field, surface integrals on vector, surface integrals, which are basically integrals of vector fields on surfaces. Okay, so the book will call this the vector version or the vector form of the surface integral. So again, before, what we do, we had the integral of f dot dr, and if you remember when we first initially introduced it, it was really the alignment between the vector in the force field and the tangent vector to the curve. Okay, and then dt, and of course we could rewrite the tangent vector as r prime of t divided by the magnitude of r prime of t dt, and then we were able to kind of do some fancy footwork and rewrite it, noting that ds, if you think about first the arc length, s equals the integral of the magnitude of r prime of t dt, then we could take the derivative of that with respect to t, and you just get the magnitude of r prime of t, right? So ds then, ds would then be the magnitude of r prime of t dt, and so I'm missing something. This would be ds right here. Okay, ds like that, sorry, and then this would be ds. Okay, so plopping this in to here gave us then the integral of f dotted with r prime of t times or all over the magnitude of r prime of t which you could rethink of as 1 all over ds dt. Okay, so this object here in the denominator, if you were to solve, I mean, it's this thing right here, right? So you could replace it with ds over dt, and you would have the integral of f dotted with r prime of t, multiplying by reciprocal, you get dt all over ds, the ds's cancel, and you have the integral of f dotted with r prime of t. R prime of t is just the derivative of r with respect to t times dt, and then the dt's canceled, and we had that form that we were introduced to for the vector version of the line integral. But I guess my long story short, the point was when we introduced it, it was this integral, which represented kind of the sum of the alignment between the force vector and the tangent vector over the curve. So what did that represent? We had some sort of curve, and it could be in space, right? So that was where I did kind of a weird, you can get as crazy as you want with these curves, I guess, to a certain extent, probably. Kind of make it go down like that. Whoops. Let's make it look a little prettier. Maybe it goes in like this, and then goes over like this, and maybe comes back up and goes down, and maybe comes over here and starts going around. I don't know. butchering it, but you get the idea, right? So what we're doing is basically cutting this curve up into a bunch of ds segments, or delta s arc length segments, and then we're considering the alignment between the tangent vector and the force field vector. So in this space, there exists a vector at every point. So in particular, at that one point on the curve, there's going to be a force field vector. Maybe put it in yellow. And what that integral is doing, because it's a dot product, this f dot t represents kind of the alignment between these two vectors. Because remember, f dot t is equal to the magnitude of f times the magnitude of t times cosine theta. So the more aligned they are, the bigger that f dot t is going to be. And our integral is basically just adding up all of these f dot t things times the line segment length. And then when we take the limit as the line segment length goes to 0, we ended up with our vector version for the line integral. Okay. So long story short, we kind of want to do the same thing, but on a surface. So how is that going to relate now to this new picture that we're dealing with? So now you can take your favorite surface. We've been using the Twinkie, maybe the front of a shoe, some sort of surface like this. And what we're going to do is immerse this in a force field as usual. And then at some point on the surface, there will be a tangent plane to it. And we can consider then the alignment kind of between the normal vector on that tangent plane. So maybe this vector is the normal vector, and then the force field vector. Okay. So everywhere in space there's going to be a force vector. We're going to add up all of those and then multiply them by the area of that little tangent plane, right? So we're going to get a bunch of these, and the book has a nice little picture somewhere. Yeah, a bunch of these kind of rectangular pictures. They're going to call it delta V, which will be a dot product between f and n, which kind of represents the height of a cube or some weird parallelepiped object, and then times the area of that base, okay, which will be delta s. From this, we're going to produce our new formula, and in order to produce that formula, the hard part is this normal vector. We need to get a formula for that. We'll have a formula for everything else. You know, it's going to be the sum of all these delta v's, and then you take the limit as the norm in the projection of the little rectangle that this thing is over top of. We want the norm of that thing to go to 0, and we'll end up with the double integral over the surface of f dotted with n ds. Okay, so ultimately that will be the kind of the thing that we want to work with, and that will be called the flux integral. You can think of it as kind of, if this surface represented maybe like a membrane, the flux integral will measure how much fluid would be going through that membrane, okay, where the force field would be representing kind of a fluid and moving across some sort of membrane. So you can imagine biology people being very interested in this sort of thing. Okay, I had a chemist once who was, for some reason, interested in containing fluids in bags, and he would need to know sort of how much fluid would, so it was a bunch of layers of bags, and he needed to figure out the fluid flow between each layer of bag for some weird thing he was doing as a chemist. So it comes up. Okay, so I need to develop a formula for this normal vector, and I need to do it in two ways, because now we have the surface z equals f of xy, but also the surface r of uv. Right, so you need two different versions of normal vectors. So let's set it up. Part A, we're talking about orientation, basically, of the surface. And what we mean by orientation is we could put these normal vectors on the top of the surface, like we have here, but if you think about inside of the surface, there's going to be a normal vector pointing down, right? So we have to pick which one we want, and therefore we're going to have like two formulas. Okay. In the homework, you're always going to be using the outward pointing normal vector, so it won't really be too painful for us, but there are a lot of formulas to deal with. Okay, so orientation of surface, part 1, we want to deal with z equals, and the book is going to call it g of xy. And the first thing you got to do, just like what we did when we were building tangent planes for these surfaces, is to rewrite your equation as z minus g of xy, and then give that a new name, big G of xyz. Okay, and then the normal vector there will just be the gradient. Okay, so the normal vector, but we want a unit normal vector, right? So it's the gradient, sure, but then you have to divide by the magnitude of the gradient. So gradient of g of x, y, z, all over the magnitude of that thing, and that will be the upward unit normal vector. And then downwards is just the negative of that. Okay. But like I said in the homework, we're always going to be using the upward unit normal vector, so don't even worry about it. Okay. So that's the z version. Then the parametric version. Of course, you're just doing cross products of partial derivatives, then dividing by the magnitude again. So it's just be, for the normal, it's the cross product of RU cross RV, cross product all over the magnitude. Again, unit normal vector. Okay, so all over the magnitude of RU cross RV. Or this would be up, or the down version is just the reverse cross product, RV cross RU. Okay, so it's never an issue where you kind of have to plot it. At least it's usually not an issue where you have to plot the thing and kind of look where is it oriented out or where is it oriented down. Usually up. Okay, usually. All right, so there's those two formulas. Now we want to build the surface integrals of the vector fields over surfaces. So using these things then, in part B, we will be able to produce the flux integrals. And basically it's just these integrals I was talking about here, where we're kind of measuring at on each rectangle the amount of flow or the amount of alignment between the normal vector and the force field vector at that particular tangent plane. And it's just that integral that I have here. Okay, so we want to flesh it out a bit. So the first version, then the z equals g of xy version, you have the double integral of f dotted with n. That's going to be this thing though, the gradient of g over the magnitude of the gradient of g, times this square root of 1 plus fx squared plus fy squared, and then dA, right? But if you think about it, the magnitude of the gradient there is just the 1 plus fx squared plus fy squared, okay? Because your gradient of this thing here, the z component, is 1, and then you got partial derivatives of g with respect to x, g with respect to y. It's going to cause a cancellation between those two objects, and so what you're going to end up with is basically just the double integral of f dotted with the gradient of g dA. Okay, so let's make sure, yeah, so you can see the cancellations here as they kind of flesh it out, and then they really write it out in terms of all the little components if you were to substitute in the components. Okay, so the gradient of g in this case, just by the way, is going to be equal to negative g with respect to x, comma, negative g with respect to y, and then 1. Okay, where did I get that? It's from just taking the gradient of that thing and plugging in the components. Okay, and this is the upward version. All right, so 2, then we got r of uv, and we want to play the same game. So now we have f dotted with the cross products. So in the numerator, it's just a normal cross product. And in the denominator, it's the magnitude of the cross product. So you have RU cross RV all over magnitude of that thing. But then ds, if you remember, what the heck is that? ds is really just the magnitude of RU cross RV times dA. So again, you get this nice little cancellation, and what you're looking at then is the integral of the dot product between the force field and this other thing, which will also be a vector. Okay, RU cross RV. And then you'll parameterize the force field in terms of u's and v's, and you'll have your full picture. Okay. Like I was saying in the homework, you're mainly going to be dealing with the upward unit normal vector. See problem 7. Upward unit normal, upward unit normal, it's always upward unit normal. So you're not going to have to worry about, at least for now, the other versions. Some points later, when we're trying to prove like Stokes' theorem or trying to establish Stokes and the divergence theorem, you may have to worry about orientation as you go around and integrate over surfaces. But for now, it's not an issue.
My voice went out apparently in the video, so now I'm doing a voiceover here. Let me try to see if it'll allow me to kind of look at what I'm doing. It's not allowing me to do that. Apparently I'm doing number 8 in WebAssign. Okay, so doing some sort of flux integral over a surface. In order to pull this off, we're going to need to rewrite z as g of x, y, z, and then get its gradient for the normal part of the double integral. So we have the f, and oftentimes you'll have to rewrite z in the dot product once you go to the actual double integral. Okay. Okay, so here's our double integral, and I don't know. So it has to be f dot n, and I'm replacing z with 1 minus x squared minus y squared. I guess here, I'm trying to figure out what I'm looking at. What is z? So it's just a elliptic paraboloid. That'll be the region I'm integrating over, that circular region there. Okay, that'll tell me the limits on my integral. Okay, so here I go, f dot n. So what the heck is f? I shouldn't have wrote that f symbol there. I'm going to have to erase that. But as you see, as I put in the vector for the force field, I'm not writing z, I'm writing 1 minus x squared minus y squared. So I finally figured out I have to erase the big F. And then I'm dotting it with the gradient of g, and you don't have to use the formulas. In the formulas you'll see it's like negative g with respect to x, that sort of thing. If you've rewritten it in the correct form by moving the 1 minus x squared minus y squared to the left side, everything should be good. Okay, so here I'm taking the dot product, and hopefully it'll simplify, and you have to use polar coordinates to do the integration. So you get x squared plus y squared plus 1, and then dA. Yeah, so I'm going to go to polar coordinates, get the double integral of r squared plus 1. Okay. Don't forget your other r from the r dr d theta. So r is from 0 to 1 because it's x squared plus y squared is 1 is the region we're integrating over. Distributing the r and then integrating. So integrate r cubed plus r, you get r to the fourth over r4 plus r squared over 2. Evaluate from 0 to 1. So you get 1/4 plus 1/2 basically. So 3/4 minus 0. You can factor out the 3/4, and then you're just integrating 1 d theta, which will be 2 pi. So 3/4 times 2 pi, and that will be 3 pi over 2. Okay. All right. So once you get the the kind of setup and you get a little practice doing these, it's no big deal. It's just setting them up correctly, and you have a bit of integration to do. Okay, let's see what's next. Number 9, another flux integral. Finding the flux across the surface, and this time I'm going sort of right to the integral. The surface is a sphere, and we only care about the first octant. X squared plus y squared plus z squared is 25. Rewriting my my surface as a 3-variable function. Unfortunately, I have to use some square roots, which means I'll probably be going to polar coordinates. Okay. So in order, I couldn't really isolate z without doing a square root. Okay, so rewriting this equation, then setting it equal to 0, so I can get my gradient for my dot product. It'll be a bit ugly, but we can do this. So the derivative of g with respect to x, firstly, I'm going to have to take the derivative of z is going to be 0, but then I need to take the derivative of that square root portion. Okay. So long story short, it's going to be x over the square root of 25 minus x squared minus y squared. You have to do a power rule, so rewrite the radical as a power of 1/2, bring down the 1/2, times 25 minus x squared minus y squared to the negative 1/2, and then times negative 2y or negative 2x. I'm going to do it right over on the right here. Here I am just checking my work, because I sort of did that in my head. So for the gradient, I need first component to be the partial with respect to x. Okay, so the partial of z is 0, and then I'm doing a power rule, bringing down the 1/2. There's a negative in front, and then the chain rule, so I have to multiply by a negative 2x, and then rewriting it, negative 2 times 1/2. Negative 1/2 is positive 1. And you're left with an x in the numerator and the square root of 25 minus x squared minus y squared in the denominator, which is, that's it. Okay, so I go ahead and now formulate my dot product. I'm looking for the force vector. I think it's given as x, y, z. So again, you have to do a replacement for z to put everything in terms of x and y. This one looks like a nightmare, but it actually isn't all that bad. there's some cancellation and okay. So anyways, yeah, there's our integral. dA. Go ahead and do your dot product. So you get x squared all over the square root of 25 minus x squared minus y squared plus y squared over the square root of 25 minus x squared minus y squared, and then plus the square root of 25 minus x squared minus y squared. And what you want to do is kind of get rid of, you're going to combine the two terms in a fancy type way to kind of get rid of this square root part. Okay. Okay, so if you combine those two fractions together, what I'm going to do is add the x squared plus y squared, and then I'm going to cheat a little bit and subtract a 25. Okay, and then it's basically kind of what you did in Calc 2. If you didn't want to do a long division, polynomial long division, you could always kind of cheat a little bit by adding and immediately subtracting something. It's that idea, and the end result is it'll get rid of the fraction, okay, because you're going to be able to now factor out a negative. So you have x squared plus y, 25 minus x squared minus y squared, all to the first power, all over 25 minus x squared minus y squared, all to the 1/2 power, and then you can reduce that entire fraction. Okay, you're still kind of left with this other material, but you know, that's just the way things are. So. One of the other problems works in a very similar way. I think I end up doing the other problem here in a little bit. But anyways, we have 25. It seems like my dot product should have plus some sort of radical on there. I must have made a mistake. Maybe I just figured out I made a mistake. But that should be plus square root 25 minus x squared minus y squared. Right now I'm figuring out what I'm integrating over. So I'm stuck in that first octant, or first quadrant. Radius is 5. So now I'm going to go to the polar coordinates. Still seems like I haven't figured out the fact that I screwed up my dot product. I'm saying I could simplify that huge expression into the negative square root 25 minus x squared minus y squared. So it'll be negative square root 25 minus x squared minus y squared. But if you go polar, you can replace the minus x squared minus y squared with minus r squared. And that's what I do. Plus 1, which seems wrong. R dr d theta. I don't know why I did that dot product wrong. Am I trying to figure? Hopefully I'm figuring it out right now that I messed that up. Yeah, you did the dot product wrong, buddy. It's like, that should not be a plus 1. That should be plus. Please tell me you figured it out. Yes, there it is. That should not be a 1. That should be square root 25 minus, I got it, minus x squared minus y squared. All of that should be. And note, if that is in fact then 25 minus x squared minus y squared, it turns into 25 minus r squared, which will cancel with the first term, just leaving you one term to integrate, which is awesome. Okay. So there's still that r sitting on the outside. So you have 25r all over the square root of 25 minus r squared. Then you could do a u sub on that, no problem. Factor of 1/2, factor of 25, so negative 25 halves. It gets pulled out of the integral. You'll have u to the negative 1/2 left, du. d theta. 25 halves. U to the negative 1 half plus 1 is positive 1 half, divided by 1 half is times 2. So you can factor that 2 out, you get negative 25 integral of u to the 1 half, but we back sub, so you get 25 minus r squared to the 1 half evaluated from 0 to the 5 d theta. So this will be negative 25 integral of 0 minus 25 to the 1 half is 5 d theta. So you just get negative 25 times negative 5 is 125 integral d theta. Integrating theta from 0 to pi over 2, because we're only in the first quadrant, get 125 pi over 2. Okay. There's a little mess up on that plus 1 thing. Sorry about that. Other than that, I have no idea what I'm doing right now. Probably pointing out this trick. I'm going to use this trick again. And I think like the last problem in this section is kind of tricky, but if you just do it in the same way as I did this problem, it works out pretty nice. So this kind of provides a template from which you can. Okay, so here's the video quiz, problem 11, which is kind of long and annoying, but like I said, if you use the same process that I used in the previous problem there, number 9, where you're kind of adding and subtracting a number. Anyways, the force field xy negative 2z, I'm going to have to replace that z when I do my flux integral here. Z is defined as the square root of a squared minus x squared minus y squared. So that thing is the top of a sphere with radius a. Okay. Here I am drawing the region I need to integrate over. Noting the radius is a. So the bounds on my integral when I go to polar coordinates eventually. I don't think we're restricted to the first quadrant or anything, I guess, in this problem. Maybe the previous problem, yours definitely stuck, I think, in one of the octants. But anyways, got to rewrite z minus the square root of a squared minus x squared minus y squared. Get the gradient for your normal vector and your flux integral, so you get x all over, just following kind of the same pattern as what we did in the last problem. You get those expressions. Let's see if I screw up the third component. It's just 1. Okay, now we set up our dot product, so force field with the gradient. So I have to rewrite z as the square root of a squared minus x squared minus y squared, which I'm doing right there. That's the part of the dot product I screwed up in the last problem. Okay, so here am I going? That's the gradient, which is really just the numerator of the normal vector. The denominator would cancel out with the ds portion of your integral. So I'm doing my dot product. I got x squared all over the square root of a squared minus x squared minus y squared plus y squared all over square root of a squared minus x squared minus y squared. You can combine those into one fraction, and it looks like that's what I'm doing. And then I'm going to pull that trick where I add in and immediately subtract a squared, like I did in the previous problem. Okay. And hope for a cancellation. Unfortunately, the cancellation isn't as nice as the last problem, but you could still play the same game. Seems like it's a pretty good way to navigate these problems. Okay. So anyways, that first term, I'm going to have to factor out the negative, do a cancellation, all that jazz, and then combine it with the third term. So I can factor out a negative, the numerator and denominator kind of cancel, and I'm just left with the negative square root of a squared minus x squared minus y squared, so I'll have negative 3 square root a squares minus x squared minus y squares left over when I'm done. And I'm not going to be able to get that thing to go away. I'm kind of trying to do it there in the red. That thing's going to turn into the negative of the square root of a squared minus x squared minus y squared, and I'm going to combine it with the negative 2, that last term, and I'll get negative 3 of them, right? Plus that first term, which isn't going to go away either. So minus 3 of these, a squares minus x squared minus y squared dA. Okay. I'm going to have to go to the polar coordinates. So going to the polar coordinates, I have 0 to a, and then 0 to 2 pi, and then a squared all over the square root of a squared minus r squared, minus 3, and there's going to be an extra r because of the r dr d theta conversion. So minus 3r times square root of a squared minus r squared. You can do u subs on both of those terms to get the job done. Okay. So do u sub a squared minus for a squared minus r squared. Du will be negative 2r dr. Okay. So basically I have two integrals I gotta kind of do right here. In each one of them you can factor out a negative 1/2, but you know, you're going to have a squared times u to the negative 1/2, and then minus 3 times u to the positive 1/2, and then of course du d theta. Tried to just write d theta probably. Du, oh whoops, it should be du d theta, not dr d theta. I'm going to go ahead and integrate those two terms. I get a squared u to the positive 1/2 divided by 1/2 is the same as multiplying by 2, minus 3 u to the 3/2 divided by 3/2, which is times 2/3. Okay. Evaluate that thing eventually when I back sub. Negative 1/2 integral a squared, there's a 2 in front of there. Yeah, let's push that in. And then back sub a squared minus r squared for u. And then the little 3's cancel in the next term, so you get minus 2 times a squared minus r squared to the 3/2. I have to evaluate from 0 to a. Okay, plugging in a firstly, both terms will be 0. And then when you plug in 0 for r squared, both terms will be, looks like the first term will be a, and then the other term will be a cubed. Okay. But yeah, you see 0 for the first two terms, and then you get 2a squared times a. Plugging in 0, you just get a. And then minus 2 times a squared minus 0 to the 3/2. A squared to the 3/2 is just a cubed. Okay, and then d theta. So cleaning that up a bit, you got 2a cubed minus 2a cubed is 0. So all of it is just going to be 0. So the answer looks like it's just going to all be 0. Yeah. Integral of 0 is 0 when you're dealing with definite integrals. Okay. Just strictly antiderivative, it would be a constant, but it's definite integral. So on the limits, you know, it'll be 1/2. C evaluated at 2 pi is still C. C evaluated at 0 is still C. So C minus C is 0. So you get the zeros for your answer. Okay. Okay, so that was the video quiz. Hopefully I can figure out how to post this online. And that will do it for me. Thank you for watching as usual. I guess in the video I'm noting that trick. Okay.